This is Random Variables Review Part 2, Combining Normal Distributions. An important fact about normal random variables: if I have two distributions that are approximately normally distributed, whether I add or subtract the two distributions, the resulting distribution is also approximately normally distributed. Let's look at an example. Suppose that the mean height of adult men in the U.S. is 70 inches, with a standard deviation of 3 inches, and that the mean height for adult women in the U.S. is 65 inches, with a standard deviation of 2.5 inches. If heights of adult men and women in the U.S. are approximately normally distributed, find the probability that a randomly selected U.S. woman is taller than a randomly selected U.S. man. How are we going to solve this? Well, here's what we have so far. So let's look at that. We have two distributions. Here is the distribution of women's heights. We were told that the women's heights were approximately normally distributed with a mean of 65 inches and a standard deviation of 2.5 inches. So the distribution looks like that. And we were told that the male heights were also approximately normally distributed with a mean of 70, didn't want to do that, with a mean of 70 inches and a standard deviation of 3 inches. So I want to find the probability that a randomly selected woman from the U.S. is taller than a randomly selected man. Well, recall, probability is successful outcomes over every total possible outcome. So I could have a woman in this region taller than 70 inches, and she could be paired with any of these men, and she'd be taller than them. I could have a woman in this region, and she could be paired with any man in this region. You get the idea. So in order to answer the question, what's the probability that a randomly selected female's height is greater than a randomly selected male's heights, I have to build a distribution of all the possible differences where the female height is greater than the male height. That's what I consider success. And then I put that over every possible difference. So we need to build a new distribution. All right, so just as a reminder, we said the female heights are approximately normally distributed with those parameters, mean 65 and standard deviation 2.5. And the male distribution of heights is approximately normal with a mean of 70 and a standard deviation of 3 inches. Again, our question of interest is, when will a randomly selected female from the U.S. be taller than a randomly selected male from the U.S.? So what we need to do is define a new distribution which represents all the possible differences in heights of a randomly selected female and a randomly selected male from the U.S. Okay? All right, so what do we know about this new distribution? What is the shape of the new distribution? Well, it's going to be approximately normally distributed because we were told that the distribution of female heights was approximately normally distributed as well as the distribution of male heights, so their difference should be approximately normally distributed. Where's the center going to be? Well, the mean of the female minus male heights will just be the mean of the female heights minus the mean of the male heights, which was 65 inches minus 70 inches, or it should be centered at -5 inches. Now that should make sense to us because what it's saying, let's put this on our distribution. It's saying that on average, females tend to be about 5 inches shorter than males. What's the spread of this new distribution that represents all the differences in female minus male heights? Well, we were told that the woman and man were randomly selected. So since they were randomly selected, their heights should be independent. So recall, standard deviations never add. Variances add only if the two groups are independent. So I've got the standard deviation of the female minus male group is equal to the square root of the variance of the females plus the variance of the males. And so that's equal to the square root of 2.5 squared plus 3 squared, which is approximately 3.9 inches. Notice here that the density function shows all the possible differences in height for a randomly selected female and male from the U.S. The difference in heights will be centered at -5 inches. The standard deviation in the difference of heights is approximately 3.9 inches. We want to find the probability that a randomly selected female from the US is taller than the randomly selected male from the US. So again, we have our distribution here that we've already looked at, and we've added one more piece of information. So we know that the female will be taller than the male when the difference is greater than 0. So I've shaded this region of the distribution. So now what I need to do is convert that to a z-score. So the probability that the female height is greater than the male height is the same as the probability that the difference in the two heights is greater than 0. Converting it to a z-score, I take my mean sample difference of 0. I see how far it is away from the mean, which is -5, scaled in standard deviation units. From that, I get a z-score of 1.28. Let's go to the calculator. Let me insert a calculator page. And go back to here. I'm going to go to Menu, Statistics, Distribution. I want to go to Normal CDF because I want the cumulative area under the normal density function. My lower bound on the scale of z was 1.28. My upper bound, as long as I go 5 standard deviations away, I should encompass most of it. I'm doing it on the scale of z, so I have a mean of 0 and a standard deviation of 1 for the standard normal curve. And I see that that cumulative area is about 0.1. And that's what we got right here. Note we use a z-distribution even though we're dealing with means because we know the population standard deviation. We use the t-distribution when the population standard deviation is unknown and I have to estimate it from my data. So in context, my conclusion here, let me move that up, the probability that a randomly selected female from the United States is taller than a randomly selected male from the US is about 0.10. Stay tuned. Our next session is on random variables, part 3, binomial and geometric distributions, and that will conclude our review of random variables.